Imagine standing on the deck of a ship, staring at an ocean so calm it looks like a polite blue blanket, and knowing that beneath you is a vertical drop so extreme it makes mountains feel insecure about their height. This is the kind of place where the ocean stops being a friendly swimming pool and starts becoming a serious personality test for both humans and machines. The Tonga Trench is not just deep water. It is a reminder that Earth still has secrets it keeps locked away, like an old diary written in a language we barely understand. If this slow exploration of why the Tonga Trench remains one of the least understood depths helps you unwind tonight, please like the video, subscribe to the Deep Sea Documentary channel, and leave a comment sharing when and where you're listening. It's so this calm science can reach more people who fall asleep to the deep ocean. As we descend in our imagination, the surface world fades fast. The light thins out, sounds grow distant, and the familiar rules of everyday life quietly resign. Up here, we worry about traffic and deadlines. Down there, the main concern is whether reality itself can survive the pressure. It is a journey that feels less like traveling through water and more like falling into another version of the planet, one that operates on its own terms and does not care if we are impressed or terrified. Spoiler alert, we are both. What makes the Tonga Trench so captivating right from the start is not just its depth, but its attitude. This is not a place that welcomes visitors. It does not sparkle. It does not glow invitingly. It simply exists, vast and silent, as if daring science to come closer and try its luck. And science, bless its curious heart, keeps accepting the challenge, even though the trench has a habit of swatting away our best efforts like a cosmic fly swatter. The deep ocean has always played this role in human imagination. Space gets all the flashy attention with rockets and stars, but the ocean is the original unknown. It is darker than space, heavier than space, and far less forgiving. At least in space, things explode dramatically. In the deep sea, they are crushed into sad little pancakes with no applause. The Tonga Trench represents the extreme end of that mystery, a place where exploration feels less like discovery and more like negotiation with a very grumpy environment. There is something humbling about realizing that we live on a planet we barely understand from the inside out. We have mapped distant galaxies, sent probes to other worlds, and yet large portions of our own ocean floor remain fuzzy, incomplete, and stubbornly elusive. The Tonga Trench sits right at the center of that contradiction. It is proof that advanced technology does not automatically translate into easy answers, especially when the subject lives under conditions that actively hate electronics. This opening chapter is not about facts and figures yet. It is about setting the emotional tone. The Tonga Trench feels less like a location and more like a boundary between what we know and what we suspect, between what we can observe and what we can only infer. It invites curiosity while simultaneously punishing it, which is a fascinating dynamic if you are a scientist and a deeply unfair one if you are a submarine. As we sink deeper, time seems to stretch. The surface world, with its sunlight and weather, feels like a distant rumour. Down here, nothing changes quickly. The trench has been patient for millions of years, and it can afford to wait a little longer for us to catch up. That patience is part of what makes it so difficult to study. It does not reveal its secrets in dramatic bursts. It hides them in subtle shifts, faint signals, and rare moments of access. And yet, we keep coming back to it. Because places like the Tonga Trench force us to confront a simple truth. Our planet is not finished surprising us. The deep ocean is not a solved puzzle or a footnote in Earth science. It is a living, shifting system that operates beyond our comfort zone. Studying it is not just about collecting data, it is about expanding the limits of what we consider possible. So this is where our journey begins. Not with answers, but with awe. Not with certainty, but with questions that feel heavy enough to sink on their own. The Tonga Trench is deep, yes, but its real depth lies in how much it reminds us that Earth is still wonderfully, frustratingly mysterious. And if that makes our curiosity nervous, good. That means we are paying attention. If you were to look at a map of the Pacific Ocean, your eyes might glide right over the Tonga Trench without much fanfare. It does not have the dramatic coastline of a continent or the obvious shape of an island chain shouting for attention. Instead, it hides in plain sight. Stretching quietly near the island nation of Tonga, east of Australia and north of New Zealand, like a massive crack in the planet that someone forgot to label in bold letters. But make no mistake, this is not a calm part of the world. This is Earth clearing its throat, loudly and repeatedly. The trench sits along a long, curved boundary where enormous slabs of Earth's crust meet. These slabs are not politely bumping into each other like shopping carts in a parking lot. They are colliding, sliding, and forcing one another downward with the kind of persistence that only geology can afford. This region is part of what scientists call the Pacific Ring of Fire, a name that already sounds like a warning label, and for good reason. Volcanoes, earthquakes, and deep ocean trenches all tend to cluster here, forming a planetary obstacle course that has been under construction for millions of years. What makes the Tonga Trench especially intense is its position along one of the fastest-moving plate boundaries on the planet. While continents drift at speeds comparable to fingernail growth, these plates are in a relative hurry, geologically speaking. That motion adds energy to everything happening in the area. It is the difference between gently pushing a door shut and slamming it with enthusiasm. The Earth does not do subtle here. It does dramatic, overachieving geology. This location also places the trench near a chain of volcanic islands that rise above the sea surface, forming a visible hint of the chaos happening below. These islands are like the freckles on Earth's face, marking where deeper processes have poked through the surface. They exist because the planet beneath them is restless, constantly rearranging itself, recycling old crust, and creating new features in the process. The trench is part of that recycling system, a place where the surface world quietly disappears into the planet's interior. Geographically, the Tonga Trench stretches in a long arc, following the edge of this plate boundary like a scar that never quite heals. Its shape is not random. It mirrors the motion and tension of the plates themselves, recording their interaction over immense spans of time. Every bend and curve is a geological sentence written slowly, one earthquake and volcanic eruption at a time. It is Earth keeping a very long and very detailed journal. Being located in this particular region also means the trench is surrounded by dynamic ocean currents, island arcs, and underwater mountains. The seafloor here is anything but flat. It is a chaotic landscape shaped by constant movement, where features rise, sink, and shift over time. Mapping this area is like trying to photograph a moving target in the dark while standing on a trampoline. The planet does not make it easy. This geographic complexity is one reason the Tonga Trench remains so difficult to fully understand. It is not isolated in a quiet corner of the ocean. It is embedded in a system that is always changing, always adjusting, and always releasing energy. The location itself generates challenges for observation and long-term study. Instruments placed here must survive not only extreme conditions, but also a restless geological setting that does not promise stability. There is also something poetically unsettling about where the trench lies in relation to human civilization. It is close enough to island communities that earthquakes and volcanic activity can have real-world consequences, yet far enough offshore that much of its behavior unfolds unseen. The trench operates backstage, influencing events without stepping into the spotlight. It is a reminder that geography does not need to be visible to be powerful. Calling this region a demolition derby is not exaggeration for humor's sake. It truly is a place where Earth's plates collide with enthusiasm, where the crust is bent, broken, and reshaped on a colossal scale. Cars crash in demolition derbies for entertainment. Plates crash here because that is simply how the planet works. No tickets sold, no cheering crowds. Oh, just relentless physics doing its job. Understanding where the Tonga Trench sits on the map is the first step toward understanding why it behaves the way it does. Location, in geology, is destiny. And this particular address happens to be in one of the most energetic, unstable, and fascinating neighborhoods Earth has to offer. Depth sounds like a simple concept. You drop a tape measure, read the number, and call it a day. The Tonga Trench laughs at that idea in a very quiet, very intimidating way. Down here, depth is not just a number. It is a moving target shaped by physics, technology, and a planet that refuses to sit still long enough to be measured politely. Saying how deep the Tonga Trench is turns out to be less like answering a trivia question and more like negotiating with reality. At extreme depths, measuring distance becomes an exercise in trust. We cannot see the bottom. Light disappears long before we get anywhere close. Cameras become decorative rather than useful. So instead, we rely on sound. Ships send pulses downward and listen for the echo bouncing back. In theory, the time it takes tells us how far away the seafloor is. In practice, the ocean bends that sound, stretches it, and sometimes sends it back with an attitude. Water temperature, salinity, and pressure all change how sound travels, and they change constantly. The ocean is basically remixing our signal before returning it. Then there is the pressure. The deeper you go, the more the weight of the ocean stacks up above you. This pressure does not just threaten equipment, it actively interferes with measurements. Instruments compress slightly, sensors behave differently, and tiny errors get magnified into big uncertainties. A fraction of a second difference in echo time can mean dozens of meters of uncertainty. At these depths, that margin matters. When scientists argue over measurements, they are not being dramatic. They are being cautious in a place where precision is brutally difficult. Gravity adds another layer of complication. The Earth's gravitational field is not perfectly uniform. Variations in mass beneath the seafloor subtly alter gravity, which in turn affects how instruments behave and how water itself distributes. That means depth is not just about vertical distance. It is influenced by invisible forces, pulling and nudging things ever so slightly out of alignment. And measuring the trench is like trying to weigh yourself on a scale that someone keeps gently tilting while the floor vibrates. Even defining what the bottom means becomes tricky. The seafloor is not a smooth, flat surface. It is a complex landscape with slopes, ridges, and depressions that can change over time. Sediment shifts. Slopes collapse. One expedition might find a deepest point that another expedition later fails to detect, not because someone was wrong, but because the seafloor itself has subtly rearranged the furniture. The trench does not provide a fixed reference point. It evolves. Technology has improved dramatically over the years, but the Tonga Trench remains a stress test for all of it. Our sonar systems must be powerful enough to reach the bottom and sensitive enough to detect a faint return signal that has travelled an enormous distance. Navigation systems must know exactly where the ship is, because a tiny horizontal error can translate into a misleading depth reading. Everything has to work perfectly, simultaneously, in one of the least cooperative environments on Earth. There is also the problem of limited access. Measuring depth accurately requires repeated passes, multiple angles, and careful calibration. This is not a place where ships can linger casually. Weather, cost, and logistical constraints limit how often and how thoroughly measurements can be taken. Each dataset is precious, but also incomplete. Scientists build a picture over time, layering information from different missions like a slowly assembling puzzle with no picture on the box. And then there is the human factor. We like definitive answers. We want a single number we can point to and feel confident about. The ocean does not share that preference. Depth measurements come with ranges, uncertainties, and footnotes. The deeper we go, the fuzzier the edges become. This is not failure. It is honesty. Pretending certainty where there is none would be far easier, but far less useful. What makes the Tonga Trench especially humbling is how it exposes the limits of our tools. These are instruments designed by some of the smartest engineers on the planet, and yet they still struggle. Not because they are poorly made, but because the environment pushes every assumption to its breaking point. Pressure warps materials, as distance weakens signals. Gravity whispers complications into every calculation. The trench does not break our technology outright. It slowly wears down its confidence. In a strange way, that difficulty is part of the trench's allure. Every new measurement is an achievement, a small victory against an environment that offers no shortcuts. Each number represents not just depth, but effort, ingenuity, and persistence. Measuring the Tonga Trench is not about conquering it. It is about carefully, respectfully asking it questions and accepting that the answers may come with uncertainty attached. So when you hear how deep the Tonga Trench is, remember that the number carries a story of sound waves travelling through darkness, of instruments holding their breath under immense pressure, and of scientists acknowledging that some places on Earth still resist being neatly quantified. Depth, down here, is not just how far you fall. It is how far our understanding has to stretch. Pressure is one of those forces that feels abstract until it suddenly is not. At the surface, we barely notice it. It presses on us constantly, politely, like a well-behaved ghost. But as you descend into the ocean, pressure stops being shy. It stacks up layer by layer, multiplying with every meter, until it becomes the dominant rule of existence. At the bottom of the Tonga Trench, pressure is not just a condition. It is the environment. It is the boss fight. To understand how extreme it gets, imagine piling the weight of several jumbo jets onto a space the size of a postage stamp. Now imagine doing that to every square inch of an object, all at once. Without mercy, and without a countdown. That is the kind of pressure we are talking about. It does not punch. It does not shove. It simply squeezes, evenly and relentlessly, until anything hollow starts reconsidering its life choices. This is why submarines built to explore such depths look less like sleek underwater ships and more like armoured bubbles. Pressure does not care about aesthetics. Flat surfaces are weak points. Corners are invitations for disaster. Even the tiniest flaw can become a fatal problem when the surrounding water is pressing inward with the patience of a glacier and the enthusiasm of a hydraulic press. The ocean is very good at finding weaknesses, and it never misses leg day. When pressure overwhelms a structure, failure is not gradual. It is sudden and spectacular in a deeply unsettling way. Implosion happens faster than human reaction time. One moment, everything exists. The next, it does not. The ocean does not negotiate. It enforces. That reality shapes every decision engineers make when designing equipment meant to survive down there. Materials are chosen not just for strength, but for how they behave when squeezed from all sides, like an unrelenting hug from a planet-sized octopus. But here is where things get truly mind-bending. Despite this overwhelming force, life exists under these conditions. Creatures living at such depths are not fighting pressure. They have made peace with it. Their bodies do not resist the squeeze because resisting would be futile. Instead, they are built to match the pressure inside and out, leaving no empty spaces for collapse to exploit, no air-filled cavities, no fragile gaps, and just tissues and fluids in perfect equilibrium. This means that animals down there are not crushed because there is nothing to crush. Their internal chemistry is adapted to function under pressure levels that would instantly destroy surface life. Proteins fold differently. Cell membranes behave differently. Even the basic machinery of life has been tuned to operate in an environment that would make most organisms give up immediately. It is not that these creatures are tougher. They are simply built for a different rulebook. Pressure also influences behavior in subtle ways. Movement becomes slower, more deliberate. Sudden bursts of speed are energetically expensive when every motion pushes against an environment that feels thick and heavy. Life adapts by conserving energy, by making efficiency a survival strategy. Down here, evolution favors patience over power. Sprinting is for amateurs and surface dwellers. What makes this even more astonishing is that pressure does not act alone. It interacts with temperature, chemistry, and time, creating a complex web of constraints that shape everything from body structure to lifespan. Pressure is the constant background note, the baseline of existence in the trench. Everything else plays on top of it. You cannot ignore it, outrun it, or outsmart it. You can only adapt or disappear. For humans, pressure is a reminder of biological limits. Our bodies are full of air spaces that make us excellent land mammals and terrible trench dwellers. Lungs, sinuses, even tiny pockets in our tissues become liabilities under extreme pressure. Without protective technology, we do not stand a chance. And even with it, our survival depends entirely on engineering holding firm against forces that are always one failure away from catastrophe. There is something humbling about that imbalance. We often imagine ourselves as dominant explorers, pushing into every corner of the planet. The pressure at the bottom of the Tonga Trench quietly disagrees. It reminds us that Earth does not bend to our ambition. We must bend to it, carefully, thoughtfully, and with a great deal of respect. In this world of crushing force, existence is not about resisting nature. It is about aligning with it so completely that the pressure becomes invisible. Life at the bottom of the trench is not heroic in the way we usually imagine heroism. It does not battle the environment, it accepts it. And in doing so, it survives where even our strongest machines must tread very, very carefully. This darkness in the deep ocean is not the cozy, lights-off kind you get in a bedroom. It is not dramatic, candlelit, or mysterious in a romantic way. It is absolute. In the Tonga Trench, darkness is so complete that the concept of light feels theoretical, like a myth passed down from distant ancestors who once lived closer to the surface. Sunlight does not fade here. It simply never arrives. The ocean absorbs and scatters light long before it has any chance of reaching these depths, leaving the trench in a permanent state of night. Sunlight behaves in water very differently than it does in air. Even in the clearest ocean, light loses strength quickly as it travels downward. Colours vanish first. Reds and oranges disappear near the surface, followed by yellows and greens, until only faint blue remains. Eventually, even that is gone. And by the time you reach extreme depths, the water has swallowed every last photon. The Tonga Trench exists beyond this point, in a realm where the sun has no jurisdiction. This absence of light has enormous consequences for life. On the surface, sunlight is the foundation of most ecosystems. It fuels photosynthesis, drives food webs, and sets daily rhythms. In the trench, none of that applies. There is no sunrise, no sunset, no seasons marked by light. Time does not reveal itself through shadows or brightness. Life must operate without the most basic environmental signal that surface organisms take for granted. Without sunlight, traditional plant life is impossible. There are no forests of seaweed, no drifting algae soaking up energy from above. Instead, life here relies on alternative strategies to survive. Food arrives from elsewhere, often drifting down slowly from the upper ocean like crumbs from a distant table. It is a sparse, unpredictable supply, and organisms have adapted to make the most of every molecule. Wastefulness is not an option when meals are rare, and the grocery store is several kilometers up. Some organisms solve the darkness problem by producing their own light. Bioluminescence becomes a tool for communication, camouflage, and hunting. In a place where vision is limited, light becomes language. A flash can mean danger, attraction, or deception, depending on the context. It is the deep-sea equivalent of texting, except the messages glow and sometimes explode into sparks. Of course, turning on a light in total darkness also risks being noticed, so every glow is a calculated risk. Eyes, when they exist, are often strange by surface standards, as some are enormous, built to capture the faintest hints of light. Others are reduced or absent entirely, because maintaining complex visual systems is expensive when there is nothing to see. Instead, other senses take over. Touch, chemical detection, and sensitivity to vibrations become far more important. The trench is a world felt more than seen. Darkness also influences behavior in unexpected ways. There is no visual horizon, no distant landmark to orient by. Movement happens in a kind of sensory bubble, where awareness extends only as far as signals can travel. This encourages a slower, more cautious approach to life. Sudden movements can attract attention you do not want. Stillness can be a form of camouflage. In the trench, doing nothing is sometimes the smartest move. Reproduction, too, is shaped by eternal night. Here, finding a mate in total darkness across vast distances is a logistical nightmare. Some species rely on chemical cues, releasing signals into the water and hoping they reach the right recipient. Others have developed strategies that sound absurd until you remember the environment they live in. In the dark, creative solutions are not optional. They are survival. Perhaps the strangest effect of this darkness is psychological, at least from a human perspective. We associate light with safety and darkness with danger. In the Tonga Trench, darkness is simply normal. There is no fear attached to it, no suspenseful build-up. It just is. Life evolves not to fight the darkness, but to accept it as the default state of reality. From the outside, this world feels alien. Creatures glowing softly in pitch-black water, navigating without sight, feeding on energy sources disconnected from the sun. It sounds like something dreamed up for a science fiction movie. But this is not another planet. It is Earth, operating under a different set of rules, quietly thriving in a place sunlight has never touched. The eternal night of the Tonga Trench is not an absence of life. It is a filter. Only organisms capable of redefining how life works can exist here. And in doing so, they remind us that light is not the only path to survival. Sometimes, evolution turns off the lights entirely and says, "Figure it out." When scientists finally manage to sample life from the depths of the Tonga Trench, the results tend to feel less like a biology lesson and more like opening a surprise package labelled "Contents may challenge your understanding of nature." The creatures found here are not simply odd-looking versions of familiar animals. They are specialists, fine-tuned for a world that operates far outside everyday experience. If surface life is written in bold, colourful strokes, trench life is written in fine print, invisible ink, and footnotes. One of the most iconic residents discovered in these depths is the amphipod. At first glance, it resembles a shrimp that has seen some things and would rather not talk about them. Pale, almost translucent, and often surprisingly large, these amphipods drift and scuttle through the trench like living punctuation marks. Their ghostly appearance is not an aesthetic choice. Our pigment is expensive to maintain, and in a world without light, colour is about as useful as sunglasses at midnight. These amphipods are scavengers, playing a crucial role as the cleanup crew of the deep. When organic material makes its long journey down from above, they are often among the first to arrive. Their bodies are adapted to make the most of infrequent meals, with efficient digestive systems and behaviours that prioritize energy conservation. They do not rush. They wait. Patience, down here, is not a virtue. It is a requirement. Fish discovered in trench environments often look like they were designed by someone who had only heard vague descriptions of fish. Soft-bodied, gelatinous, and sometimes lacking the rigid bones we associate with vertebrates, these animals challenge our assumptions about what a fish should be. And their tissues are flexible, allowing them to function where stiffness would be a liability. Think less armoured knights, more well-engineered stress ball. Some of these fish produce natural antifreeze-like compounds in their cells, allowing their biological processes to continue without falling apart under extreme conditions. Their muscles and enzymes operate in ways that would fail instantly in surface species. This is not just adaptation. It is a complete rewrite of how a vertebrate body can function. Nature did not tweak the settings here. It installed a different operating system. Then there are the true minimalists, microorganisms. Bacteria and archaea thrive in the trench, quietly running chemical reactions that look downright rude from a human perspective. Compounds we consider toxic or uninhabitable are, to them, an all-you-can-eat buffet. These microbes use chemical energy instead of sunlight, breaking down substances released from the earth itself or from decaying material drifting down from above. These microscopic communities form the invisible backbone of the trench ecosystem. They recycle nutrients, support larger organisms, and keep energy moving through the system. Without them, the trench would be a biological dead end. Instead, it hums along quietly, powered by chemistry rather than photosynthesis. If the surface ocean runs on solar panels, the trench runs on batteries buried deep in the planet. Some organisms found here display extreme forms of specialization. Certain species appear to exist only in these depths, never venturing upward. They are not explorers. They are homebodies, ill-evolved for a niche so specific that leaving it would be a death sentence. This level of specialization makes them fascinating to scientists and fragile in the face of change. Their entire existence is tied to conditions that exist almost nowhere else. Reproduction among trench organisms often reflects the challenges of their environment. Many produce fewer offspring, investing more energy into each one. Others rely on larvae that drift upward before eventually settling back down, like biological boomerangs. These strategies are shaped by isolation, low population densities, and the simple difficulty of finding another living thing in a vast, dark space. What unites all these life forms is efficiency. Nothing is wasted. Every structure, every behavior, every chemical process serves a purpose. Evolution here does not reward excess, and it rewards survival under constraints that would instantly overwhelm most life on Earth. These organisms are not freaks of nature. They are success stories, written in a language we are still learning to read. Studying these creatures does more than satisfy curiosity. It expands our understanding of what life can be. It challenges assumptions about where biology can function and how flexible it can be. The trench does not host life, despite its extreme conditions. It hosts life because evolution found a way to make those conditions work. So when we meet these ghostly amphipods and chemical-loving bacteria, we are not just meeting oddities. We are meeting proof. Proof that life does not need comfort, light, or familiarity. Sometimes, all it needs is enough time and a willingness to adapt in directions we never thought to look. One of the most frustrating things about studying the Tonga Trench is not what scientists have discovered, but what they have not. When compared to other deep trenches, the list of identified species here feels surprisingly short. This does not mean the trench is empty. It means our window into it is narrow, foggy, and occasionally slammed shut by technical reality. Imagine trying to catalogue wildlife in a rainforest using a single flashlight for 10 minutes during a thunderstorm. That is roughly the level of challenge involved. The first reason for this scarcity is access. Expeditions to extreme depths are rare, expensive, and risky. Each mission requires years of planning, specialized equipment, and a small army of experts. As a result, only a handful of direct biological surveys have ever taken place in the Tonga Trench, and every descent samples an enormous environment through a very tiny keyhole. If life does not wander into that keyhole at the right moment, it remains invisible to science. Sampling methods themselves introduce limitations. Nets, traps, and remote vehicles all have biases. They collect certain sizes, certain behaviors, certain types of organisms more easily than others. Slow-moving scavengers might be overrepresented. Elusive or fragile species may never be captured at all. It is not that these creatures are absent. They are simply very good at not being caught, which, in evolutionary terms, is an excellent skill to have. Then there is the problem of scale. The Tonga Trench is vast, and life within it is likely unevenly distributed. Resources are patchy, habitats vary. Some areas may host thriving communities, while others are biological deserts. Without extensive, repeated sampling across many locations, it is nearly impossible to know which picture is more accurate. Scientists are often left guessing whether a low count reflects true scarcity or simply unlucky sampling. Preservation adds another layer of complication. Organisms adapted to extreme conditions do not always survive the journey back to the surface. Changes in pressure and temperature can damage tissues alter structures, or destroy delicate features that would help with identification. What arrives in the lab may be a distorted version of what once lived in the trench. Interpreting these samples requires caution and sometimes educated imagination. The lack of data also affects how scientists frame their questions. With so few confirmed species, and it becomes difficult to identify patterns, relationships, or trends. Is this trench uniquely sparse, or does it simply host life forms we have not learned how to detect yet? Are certain groups absent, or have we just not met them? Each unanswered question spawns more, creating a scientific feedback loop of curiosity and frustration. This uncertainty can be unsettling. Science thrives on evidence, repetition, and verification. The Tonga Trench offers none of these in abundance. Instead, it offers hints, fragments, occasional surprises that refuse to fit neatly into existing frameworks. Researchers must be comfortable working with incomplete information, knowing that any conclusion is provisional and subject to revision with the next rare expedition. There is also the issue of comparison. Other trenches have been studied more extensively, providing a richer biological record. This can create the illusion that the Tonga Trench is less lively by comparison. In reality, it may simply be less observed. Absence of evidence, as scientists love to remind everyone, is not evidence of absence. Unfortunately, that reminder does not make grant proposals any easier to write. The detective analogy fits because scientists investigating the trench are piecing together a case from scattered clues. A single specimen here, a chemical signature there, a fleeting glimpse on a camera feed that vanishes before anyone can say hello. There are no witnesses willing to testify, no crime scene neatly taped off. Just a lot of unanswered questions and a strong suspicion that something important is happening out of sight. Yet this lack of information is not purely negative. It highlights how much remains to be discovered. It keeps the trench from becoming a closed book. Each unknown is an invitation, a reminder that exploration is not about confirming what we already know, but about confronting what we do not. The Tonga Trench resists easy conclusions, and that resistance is part of its scientific value. In the end, the scarcity of known life in the Tonga Trench says more about our limitations than about the trench itself. It reflects how hard it is to study extreme environments and how much patience deep science requires. The clues are out there, scattered across kilometers of dark water. The challenge is not whether life exists, but whether we can learn to find it without assuming it should behave in familiar ways. Beneath the calm surface of the Pacific, as the Tonga Trench marks a place where the Earth is actively folding in on itself. This is not a metaphor. One massive slab of the planet is literally being pushed downward into the mantle, disappearing slowly but relentlessly. This process is called subduction, and in the Tonga Trench, it happens with a level of intensity that makes geologists both excited and slightly nervous. To picture subduction, imagine a slow-motion conveyor belt made of rock. One plate moves forward and is forced beneath another, bending as it goes. But unlike a conveyor belt, this slab does not glide smoothly. It scrapes, locks, bends, and eventually snaps. Rock, despite its reputation for being solid and dependable, behaves more like a stubborn piece of plastic when stressed over long periods. It resists, stores energy, and then releases it suddenly when it can no longer cope. That sudden release is an earthquake. In the Tonga Trench, this sinking plate does not slide down at a gentle angle. It plunges steeply, diving into the planet like it has somewhere important to be. This steep descent changes how stress builds up and where it is released. Instead of earthquakes being limited to shallow regions, they can occur far deeper than usual, sending seismic waves through the Earth's interior like a planetary ringtone nobody can silence. As the plate bends downward, it fractures internally. These fractures are not visible cracks you could point to on a map. They are zones of weakness forming deep within the rock, where pressure and temperature are pushing materials to their limits. When these zones finally give way, the energy released does not stay local, and it radiates outward, traveling thousands of kilometers through the Earth. Seismic stations across the Pacific feel it, even if nothing dramatic happens at the surface. This is why earthquakes associated with the Tonga Trench can have effects far beyond the trench itself. The Pacific Basin is essentially a giant bowl of connected geology. Vibrations generated in one intense corner can echo across the entire structure. It is Earth reminding us that its systems are interconnected in ways that ignore national borders and human expectations. Another key feature of subduction zones is the buildup of stress over time. Plates do not move smoothly past one another, they get stuck. Friction holds them in place while motion continues elsewhere, quietly loading energy like a compressed spring. When that spring finally releases, the result can be sudden and powerful. The trench is not constantly shaking because energy is always being stored before it is released. Earthquakes are not random tantrums, they are overdue payments. The depth at which these earthquakes occur also tells scientists something important. As the plate descends, conditions change dramatically. Temperature increases, pressure rises, minerals transform. These changes affect how rocks break and slide. By studying earthquake patterns, researchers can infer what is happening inside the planet, far beyond direct observation. Each tremor is a message from a place we cannot visit, written in vibrations instead of words. What makes the Tonga Trench particularly fascinating is how efficiently it sends these messages. The steeply sinking plate creates a clear seismic signature, as allowing scientists to track the plate's journey downward. It is like watching a shadow move behind a curtain. You cannot see the object itself, but its outline tells you a lot about its shape and motion. Subduction also plays a role in Earth's long-term balance. As plates sink, they carry surface materials into the mantle, where they are transformed and eventually recycled. This is part of how the planet manages heat and maintains its dynamic nature. Earth is not a static rock floating through space. It is an active system, constantly renewing itself. And subduction zones are one of its primary engines. For people living around the Pacific, this process is both distant and deeply relevant. Most of the time it happens quietly, far below the ocean floor. But when energy is released suddenly, the effects can be felt across entire regions. The trench may be remote, but its influence is anything but. Understanding how subduction works in the Tonga Trench helps explain why this area is so seismically powerful. It is not chaos. It is physics playing out on a colossal scale. Plates sink, stress builds, energy releases, and the planet continues its slow, restless motion. The earthquakes that ripple across the Pacific are not accidents. They are the sound of Earth doing what it has always done, long before we were listening. It is tempting to think of earthquakes as local events. A fault slips, the ground shakes, the news reports it, and life goes on. But in reality, seismic activity behaves more like a conversation than a monologue. When the Earth moves in one place, other places listen. The Tonga Trench plays an outsized role in this global dialogue, but not because it is loud all the time, but because of how deeply its movements connect to the planet's internal structure. When earthquakes occur near the trench, the energy released does not simply fade away after rattling the surrounding region. Seismic waves travel through the Earth's interior, bouncing, bending, and refracting as they encounter different layers. These waves can circle the planet multiple times, their paths subtly altered by variations in temperature, composition, and density deep inside Earth. In this way, the Tonga Trench becomes a source of information about the planet's inner workings, even when its influence is felt thousands of kilometers away. Seismologists around the world pay close attention to activity originating in this region because it generates signals that penetrate unusually deep. These deep origin waves help scientists map parts of the mantle that would otherwise remain mysterious. Every tremor is like tapping on a wall and listening carefully to the echo, trying to infer what lies behind it. The trench does not just cause earthquakes. It provides data that reshape our understanding of the entire planet. This influence extends beyond scientific curiosity. Seismic energy traveling through the Earth can interact with distant fault systems in complex ways. While one earthquake does not directly cause another on the opposite side of the planet, it can alter stress conditions elsewhere, nudging faults closer to or further from failure. Think of it as adjusting the tension on a spiderweb. Pluck one strand, and the whole structure feels it, even if nothing snaps immediately. Yet the deep ocean plays a crucial role in this process because it hides some of the most powerful geological interactions on Earth. Unlike continental faults, which are monitored closely and often visibly scar the landscape, deep-sea systems operate out of sight. Their influence, however, is no less real. The Tonga Trench is a reminder that some of the planet's most important processes happen far from where we can easily observe them. Seismic networks on land rely on signals that have traveled through both solid rock and the ocean-covered crust. By analyzing how waves from trench-related earthquakes arrive at distant stations, scientists can refine models of Earth's internal structure. This improves not only our understanding of tectonics, but also our ability to assess seismic risk in regions far removed from the trench itself. So, in a quiet way, the trench contributes to global preparedness. There is also a temporal dimension to this influence. The trench has been active for millions of years, shaping seismic patterns over geological time. Its long-term behavior affects how stress is distributed across the Pacific region, influencing where energy accumulates and how it is eventually released. Earthquakes today are part of a story that began long before humans were around to feel them. What makes this particularly humbling is how disconnected cause and effect can feel. A powerful earthquake in the deep ocean may go unnoticed by most people, yet the data it generates could help scientists better understand seismic hazards elsewhere. Conversely, a quake felt strongly on land may owe part of its context to deep, distant processes operating beneath the sea. The Earth does not compartmentalize its activity. Everything is connected. This interconnectedness challenges how we think about natural disasters. It encourages a shift from viewing earthquakes as isolated incidents to seeing them as expressions of a dynamic global system. The Tonga Trench is one of the places where that system is especially active, quietly influencing patterns that extend far beyond its dark waters. In the end, the trench's role in global seismic activity is a lesson in scale and perspective. It shows us that the deep ocean is not a passive backdrop to the planet's drama. It is an active participant, shaping how energy moves through Earth and how the planet releases its built-up stress. Even when we cannot see it, even when it feels impossibly distant, the Tonga Trench is very much part of Earth's emotional life. It is sending tremors through a planet that is never truly still. Exploring the Tonga Trench Sounds straightforward in theory. Build a machine, point it downward, and collect data. In reality, this plan collapses almost immediately under the weight of physics, logistics, and budget spreadsheets that quietly scream for mercy. The deep ocean is not impressed by ambition. It demands preparation, redundancy, and a willingness to accept that even the best technology may fail without warning. One of the first obstacles is materials. At extreme depths, even metals behave differently. Strength alone is not enough. Materials must resist long-term stress without deforming, cracking, or reacting chemically with the surrounding environment. Every bolt, seal, and window becomes a potential point of failure. Engineers must assume that if something can break, and the ocean will find a way to break it, usually at the worst possible moment. Designing equipment for these conditions often means sacrificing versatility for survival. Deep diving vehicles are specialized to the point of being almost single-purpose. They are heavy, slow, and expensive, built not to explore widely, but to endure. This limits how much data can be gathered in a single mission. You cannot simply add more sensors or extend the mission indefinitely. Every addition increases complexity and risk. Human presence adds another layer of challenge. Keeping a person alive at such depths requires life support systems that must function flawlessly. Oxygen, temperature control, communication, and emergency systems all need to operate inside a sealed environment that cannot afford even a microscopic leak. The margin for error is effectively zero. Unlike in space, where failures can sometimes be mitigated, the deep ocean offers no rescue options. If something goes wrong, help is very far away and moving very slowly. Uncrewed vehicles avoid some of these risks, but they introduce others. Remote systems must operate autonomously for long periods, making decisions without real-time human input. Communication delays and signal loss are common, especially at extreme depths. When contact is lost, recovery is not guaranteed. The ocean does not return lost equipment politely. It keeps souvenirs. Cost is an unavoidable reality. Building and operating deep-sea exploration vehicles requires massive investment. Research ships, support crews, fuel, maintenance, and mission planning all add up quickly. Each descent represents a significant financial gamble. Funding agencies must weigh the potential scientific payoff against the very real possibility of failure. This limits how often missions can be attempted and how ambitious they can be. Testing equipment for these conditions is also difficult. You cannot easily simulate the full environment of the Tonga Trench in a laboratory. Pressure chambers can approximate certain aspects, but they cannot replicate the full complexity of the deep ocean. This means some testing happens in the real environment, where mistakes are costly. Engineers often learn what does not work by watching something fail, which is an expensive way to gain knowledge. Navigation presents another challenge. Deep underwater, traditional positioning systems are useless. Vehicles must rely on inertial navigation, acoustic signals, and careful planning. Errors accumulate over time, making precise positioning difficult. Knowing exactly where you are and exactly where you have been becomes a complex puzzle. Mapping and sampling depend on accuracy that is hard to maintain under these conditions. Then there is the simple fact that the ocean is unpredictable. Currents, sediment movement, and geological activity can interfere with missions in ways that cannot be fully anticipated. A vehicle might encounter unexpected terrain or conditions that force an early return. Plans must remain flexible, and flexibility often means compromising scientific goals. All of this leads to a humbling conclusion. Our technology, impressive as it is, operates on the ocean's terms, not the other way around. Confidence must be balanced with caution, as overconfidence leads to failure. The deep ocean does not reward shortcuts or assumptions, it exposes them. Despite these challenges, exploration continues because the potential rewards are enormous. Each successful mission expands our understanding of Earth and pushes the boundaries of engineering. Failures, while costly, provide lessons that drive improvement. Progress is slow, but it is real. Sending humans or machines into the Tonga Trench is difficult, not because we lack intelligence or creativity, but because we are attempting to operate in an environment fundamentally hostile to our existence. The ocean does not care how advanced we think we are. It responds only to physics. Respecting that reality is the first step toward meaningful exploration. And the reason every descent into the trench is both a scientific endeavor and an act of profound humility. Every expedition to the Tonga Trench begins with optimism and ends with humility. Scientists set out with carefully defined goals, detailed plans, and a checklist of questions they hope to answer. They return with data, samples, and recordings that are undeniably valuable, yet somehow incomplete. The trench has a way of giving just enough information to be fascinating while withholding enough to remain deeply annoying, which, from a scientific perspective, is both a curse and a gift. Early expeditions relied heavily on indirect observations. Long before vehicles could descend safely, researchers used seismic readings, gravity measurements, and water chemistry to infer what might be happening below. These early efforts established the trench as an extreme environment, but they also revealed how limited surface-based observations could be. It was like trying to understand a city by listening to the vibrations of traffic through the ground. You could tell something was happening, but not what it looked like. As technology improved, direct sampling became possible, though still rare. Deep-sea landers were among the first tools to physically reach the trench floor. These robotic platforms were dropped from ships and left to sit quietly, collecting data before releasing weights and floating back to the surface. The information they returned was groundbreaking, confirming the presence of life and providing snapshots of environmental conditions. At the same time, they raised new questions. Why were certain organisms present while others were absent? Were these samples representative, or just lucky encounters? Crude descents, when they occurred, offered an even more intimate glimpse. Seeing the trench floor directly, even through thick viewports, changed how scientists thought about it. Subtle features that might be missed by instruments alone became apparent. Textures, movement, and spatial relationships added context to raw data. But these missions were brief. Time at depth was limited, and every observation felt like the first page of a book that immediately slammed shut. One recurring theme across expeditions is surprise. Instruments often detected unexpected chemical signals, unusual biological activity, or geological features that did not fit existing models. These surprises forced scientists to revise assumptions and rethink theories. Instead of confirming what was already suspected, the trench repeatedly challenged it. Each mission became less about answers and more about refining the right questions to ask next. Another challenge was comparison. Data collected during different expeditions were often difficult to reconcile. Variations in equipment, sampling locations, and mission duration made direct comparisons tricky. What looked like a pattern in one dataset might disappear in another. Scientists had to be careful not to overinterpret limited information. The trench punished premature conclusions with conflicting evidence. Samples brought back to the surface added their own complications. But biological specimens sometimes displayed features that were hard to interpret without knowing how they behaved in their natural environment. Chemical samples hinted at processes that could not be directly observed. Geological data suggested forces at work that could only be modelled, not witnessed. Each sample was like a postcard from a place no one could stay long enough to truly know. Despite these limitations, every expedition contributed something essential. They established baselines, tested equipment, and demonstrated what was possible. Even failures proved useful, revealing design flaws or environmental hazards that informed future missions. Progress came not from single breakthroughs, but from accumulation. Knowledge built slowly, layer by layer, much like sediment settling on the trench floor. Well, what makes these expeditions particularly compelling is how often they ended with more uncertainty than clarity. A mission might confirm that life exists at extreme depths, only to raise questions about how widespread it is. It might map a section of the trench, only to reveal features that demand closer inspection. Scientists returned not triumphant, but curious, already planning what they would do differently next time. This pattern can be frustrating, especially in a scientific culture that values clear results. But it also reflects the reality of exploration at the edge of the unknown. The Tonga Trench is not a puzzle designed to be solved quickly. It is a system too complex and too remote for easy conclusions. Each expedition is a conversation, not a verdict. In that sense, the trench's scientific souvenir shop is well stocked. But researchers come back with data instead of trinkets, questions instead of answers, and a renewed respect for how much remains unseen. The value of these missions lies not in closing chapters, but in opening new ones. The Tonga Trench does not reveal its secrets all at once. It parcels them out sparingly, ensuring that curiosity never quite runs out. If the Tonga Trench were a living organism, its chemistry would be its bloodstream, invisible, constantly moving, and absolutely essential. The chemical processes happening in these depths quietly influence far more than the dark water they occupy. Chemistry here does not behave like it does in surface waters. It slows down, concentrates, and follows pathways shaped by pressure, isolation, and time. This is not the ocean's fast-paced upper layer where sunlight fuels rapid cycles. And this is the deep ocean's long game. Nutrients reaching the trench mostly arrive as leftovers from above. Tiny particles of organic material drift downward over weeks, months, sometimes longer, slowly raining into the depths. By the time they arrive, they are sparse and heavily processed, the nutritional equivalent of crumbs swept under a cosmic couch. Yet even these remnants matter. Once they reach the trench, they become part of a tightly controlled recycling system where nothing goes to waste. As organic material breaks down, it releases nutrients back into the surrounding water and sediment. These nutrients do not disperse quickly. The trench's shape and depth encourage them to linger, creating localized chemical environments that differ from the surrounding ocean. Where this slow accumulation can support microbial communities and influence how elements move through the deep sea. The trench becomes less of a dead end and more of a holding zone, quietly participating in the ocean's nutrient economy. Metals play an equally intriguing role. Elements like iron, manganese, and others are released from sediments through chemical reactions, driven by pressure and limited oxygen. In surface waters, these metals are often quickly consumed or dispersed. In the trench, they can accumulate or cycle slowly between different chemical states. This affects not only local chemistry, but potentially the availability of these elements to the broader ocean if currents eventually redistribute them. Carbon is where things get especially interesting. And the trench acts as a deep repository for carbon-rich material that sinks from above. Once there, carbon can be stored for long periods, effectively removed from short-term cycling. This process contributes to Earth's natural carbon regulation, locking away carbon in places far removed from the atmosphere. It is not flashy, but over geological timescales, it matters. Chemical reactions in the trench are shaped by extreme pressure, which alters how molecules interact. Reactions that proceed easily at the surface may slow down or change behavior entirely. Pressure affects solubility, reaction rates, and even the structure of water itself. Chemists studying trench samples often find that familiar rules need adjustment. The deep ocean does not break chemistry, but it certainly bends it. Another factor is oxygen availability. At extreme depths, as oxygen levels can be low, forcing chemical processes to follow alternative pathways. This creates distinct chemical signatures that help scientists trace how water masses move and mix over time. By analyzing these signatures, researchers can infer connections between deep trenches and larger ocean circulation patterns. The trench may be isolated, but it is not disconnected. Sediments at the bottom of the trench are active chemical zones. As material accumulates, it undergoes slow transformations, releasing gases and altering mineral composition. These processes can influence the chemistry of the overlying water, creating feedback loops between geology and ocean chemistry. It is a quiet exchange, but one that persists over immense spans of time. What makes this chemistry globally relevant is scale. The ocean is vast, and in trenches like Tonga represent only a fraction of its volume. But they operate continuously, over millions of years. Small chemical effects, applied consistently, can influence large systems. Understanding these processes helps scientists build more accurate models of ocean behavior, climate interactions, and long-term planetary change. Studying trench chemistry is also technically demanding. Samples must be collected without contamination, preserved under extreme conditions, and analyzed with care. Even slight changes during retrieval can alter chemical balances. This makes every dataset precious and every conclusion tentative. The chemistry of the trench resists easy interpretation, much like the trench itself. In the end, the Tonga Trench is not just a physical feature or a biological curiosity. It is a chemical participant in Earth's systems, quietly shaping how elements move through the planet's largest reservoir. While it may seem remote and isolated, its chemistry reminds us that the deep ocean is not separate from the rest of the world. It is part of a connected, planetary-scale process, one slow reaction at a time. High above the Tonga Trench, debates about carbon often feel loud, urgent, and full of charts. Down in the trench, carbon behaves very differently. There are no headlines, no policy meetings, no dramatic announcements. Carbon simply sinks, settles, and waits. This quiet process makes deep trenches like Tonga an overlooked but important part of Earth's long-term carbon story. Carbon enters the ocean in many forms, but only a fraction ever makes it to extreme depths. Most is recycled quickly near the surface, consumed by organisms or released back into the atmosphere. The carbon that does reach the trench is the stubborn remainder, material that has survived grazing, decay, and dilution during its long descent. By the time it arrives, it is no longer fast-moving carbon. It is patient carbon. Once in the trench, carbon becomes part of a slow system of storage and transformation. Organic carbon, can be buried in sediments, where it may remain for thousands to millions of years. This burial effectively removes carbon from short-term cycling, reducing how much can interact with the atmosphere. It is not a solution to modern emissions, but it is part of the planet's natural balancing act, one that operates on timescales far longer than human attention spans. The trench's depth and shape enhance this storage, and material that falls in does not easily escape. Steep walls and limited circulation mean that carbon-rich sediments are more likely to stay put. Over time, layers accumulate, locking carbon away beneath additional deposits. Each layer is a page in Earth's carbon history, written slowly and without commentary. Microbial activity plays a role in determining carbon's fate. Some carbon is broken down further, converted into different chemical forms, or incorporated into microbial biomass. Other portions resist degradation and remain intact. The balance between these pathways depends on local conditions, including pressure and chemistry. The trench does not treat all carbon equally. It sorts, transforms, and archives it. This deep storage matters because it influences the overall carbon budget of the ocean. The ocean is Earth's largest active carbon reservoir, and even small shifts in how carbon is stored or released can have long-term effects. Trenches contribute by acting as sinks, quietly capturing carbon that might otherwise circulate back toward the surface. Their impact is subtle but persistent. Understanding this role is challenging. Measuring carbon storage in the trench requires sediment cores, chemical analyses, and careful interpretation. Data are sparse, and uncertainty is high. Scientists must piece together a picture from limited samples, extrapolating cautiously. The trench does not offer easy answers, only hints that suggest its importance. What makes this particularly intriguing is how disconnected it feels from human activity, as the processes operating in the Tonga Trench began long before industrialization and will continue long after current debates have faded. Yet they interact with the same global system we are influencing today. The trench is not responding to policy. It is responding to physics, chemistry, and time. This perspective can be both comforting and sobering. Comforting, because Earth has natural mechanisms that help regulate carbon. Sobering, because those mechanisms operate far too slowly to offset rapid changes. The trench is a reminder that while the planet has ways of managing carbon, they are not designed for sudden spikes. Studying how trenches store carbon also helps scientists understand past climate conditions. Layers of sediment preserve records of how much carbon entered the deep ocean at different times. By analysing these records, researchers can infer changes in productivity, circulation, and climate over geological timescales. The trench becomes a historical archive, storing not just carbon, but information. In the end, the Tonga Trench's role in the carbon cycle is defined by quiet persistence. While the surface world argues, measures, and negotiates, the trench continues doing what it has always done. Carbon sinks, settles, and stays. It is not dramatic. It does not solve our problems. But it is part of the system that keeps Earth in balance over the long haul. And in a planet defined by slow, interconnected processes, that quiet contribution matters more than it first appears. One of the most unsettling truths about the Tonga Trench is not how extreme it is, but how poorly we understand what it takes to survive there over time. We can identify organisms, yes, analyze their chemistry, and describe their adaptations, but longevity remains a mystery. How long do these creatures live? How stable are their populations? What happens to them over decades, centuries, or longer? The trench keeps these answers close, offering only brief glimpses instead of long-term narratives. Studying long-term survival requires observation over extended periods, and that is precisely what the trench makes nearly impossible. Instruments cannot remain indefinitely without maintenance. Expeditions are short. Samples are snapshots taken from a system that operates on timescales far beyond our ability to monitor continuously. We are trying to understand marathon runners by watching them sprint past once. Life at these depths exists under conditions that would normally shorten lifespans. Extreme pressure, limited food, and slow metabolism all shape how organisms grow, reproduce, and age. Some species may live surprisingly long lives, conserving energy and minimizing damage over time. Others may follow entirely different strategies, cycling through generations slowly but steadily. Without long-term data, these possibilities remain hypotheses rather than conclusions. What we do know suggests that life in the trench operates under a fundamentally different set of biological rules. Growth is often slow. Reproduction may be infrequent. Energy budgets are tightly controlled. These traits challenge surface-based assumptions that faster growth and frequent reproduction are universal measures of success. In the trench, survival favors efficiency, stability, and patience. This has implications beyond curiosity. Our understanding how organisms persist under constant stress could inform broader biological questions. How do cells maintain integrity under extreme conditions? How is damage repaired when resources are scarce? What mechanisms prevent proteins from breaking down over long periods? The trench offers natural experiments that biology cannot easily replicate in laboratories. Another unknown is how resilient these organisms are to change. Life adapted to stable, extreme conditions may be particularly sensitive to disruption. Small shifts in chemistry or food supply could have outsized effects. Without knowing how populations fluctuate naturally, it is difficult to predict how they might respond to external influences. The trench may be both remarkably robust and surprisingly fragile, and a combination that complicates conservation and management efforts. Evolutionary timescales add another layer of complexity. Life in the trench has had millions of years to adapt, yet the pace of change there may be slow. Limited energy availability could reduce mutation rates or slow selection processes. Alternatively, extreme conditions might amplify the consequences of small changes. Without genetic timelines and population histories, these questions remain open. The challenge of studying long-term survival also forces scientists to confront the limits of inference. Observing a well-adapted organism does not automatically reveal how it got there, or how stable its existence is. The trench teaches humility. It reminds us that adaptation is not always visible, and that survival can take forms that do not fit our expectations. Despite these uncertainties, the existence of life at such depths already rewrites what we thought was possible. It expands the known boundaries of biology and forces us to reconsider where life might exist elsewhere. If organisms can thrive under constant pressure, darkness, and scarcity, then the definition of habitable environments becomes far broader than once imagined. This perspective reaches beyond Earth. Understanding long-term survival in extreme environments informs how scientists think about life on other worlds. The trench becomes a reference point, a proof of concept that life can persist in places once dismissed as too hostile. In that sense, the mystery itself is valuable. It keeps the door open to possibilities we have not yet conceived. Ultimately, thus the question of long-term survival in the Tonga Trench remains unanswered, not because it is unimportant, but because it is difficult. The trench resists prolonged observation, revealing its inhabitants only briefly. Yet even these brief encounters suggest a form of life that is patient, efficient, and resilient in ways we are only beginning to understand. Life in the trench does not just survive despite extreme conditions, it thrives by embracing them, and in doing so, it quietly challenges our assumptions about what life needs, how it endures, and where it can persist over the long haul. In the deep ocean, sound is king. Light gives up early, radio waves barely get a foot in the door, and vision becomes a luxury. Sound, on the other hand, travels far and fast through water, making it the primary way we explore, communicate, and map the seafloor. At least that is the plan. In the Tonga Trench, sound still rules, but it does so with a mischievous streak, bending, warping, and occasionally misleading the very tools designed to rely on it. Sonar works by sending sound pulses through the water and listening for their return. The time it takes for the echo to come back helps determine distance and shape. In shallow or moderately deep waters, this process is relatively straightforward. In extreme depths, it becomes a complex dance between physics and uncertainty. The ocean is not a uniform medium. Its properties change with depth, and those changes alter how sound moves. Temperature is one major factor. Sound travels faster in warmer water and slower in colder water. In the deep ocean, temperatures are low and relatively stable, but subtle gradients still exist. Yet these gradients can bend sound waves, curving their paths rather than letting them travel straight down and back up. As a result, echoes may arrive earlier or later than expected, distorting distance estimates. The trench essentially puts sonar through a funhouse mirror. Pressure adds another layer of complexity. As depth increases, pressure changes the physical properties of water, affecting how sound waves propagate. The higher density alters speed and direction in ways that are difficult to predict precisely. Models can account for these effects, but small inaccuracies accumulate over long distances. By the time a sound wave has travelled several kilometres down and back, even tiny errors can become significant. Salinity also plays a role. Variations in salt concentration influence sound speed. And while deep waters are relatively uniform compared to surface layers, they are not perfectly consistent. Mixing, currents, and chemical processes introduce subtle differences. These variations act like invisible lenses, refracting sound in unexpected ways. The ocean becomes an acoustic maze, and sonar pulses must navigate it blind. The shape of the trench itself complicates matters further. Steep walls, uneven surfaces, and complex terrain scatter sound waves in multiple directions. Instead of a clean echo returning to the source, signals can bounce, split, or weaken. Some energy is absorbed by soft sediments. Some is reflected at odd angles. The result is data that require careful interpretation and often come with asterisks attached. At extreme depths, the sheer distance involved is a challenge. Sound waves weaken as they travel. By the time an echo returns from the bottom of the trench, it may be faint, noisy, or partially lost. Distinguishing a real signal from background noise becomes difficult. This noise can come from natural sources, equipment vibrations, or even distant human activity. The ocean is rarely silent, even in its deepest parts. Mapping the trench, therefore, is not a matter of a single pass. It requires repeated surveys, overlapping data, and constant calibration. Even then, uncertainty remains. Different sonar systems may produce slightly different results. Interpreting these discrepancies demands expertise and caution. Scientists must resist the temptation to smooth out irregularities that may represent real features. This acoustic difficulty is why maps of the trench often appear incomplete or imprecise. It is not a lack of effort. It is the environment pushing back, The trench does not present itself neatly. It refuses to be summarized easily, forcing researchers to accept approximation rather than perfection. Ironically, this resistance makes sound even more valuable. By studying how sound behaves in these conditions, scientists learn more about the ocean itself. Variations in sound speed reveal information about water structure and movement. Sonar becomes both a mapping tool and a diagnostic instrument, offering insights beyond topography. Still, the frustration remains. The trench is one of the most challenging places on Earth to map accurately. It turns a dependable technology into a negotiation, reminding us that even our best tools have limits. The ocean does not sabotage sonar out of spite. It simply follows the rules of physics, even when those rules make our lives difficult. In the end, the Tonga Trench's refusal to be mapped politely is part of its character. It is a place where sound is essential but unreliable, where echoes tell partial truths, and where certainty is always just out of reach. For scientists, this is not a defeat. It is an invitation to listen more carefully, question more deeply, and accept that some landscapes demand patience rather than precision. At first glance, the Tonga Trench seems like the ultimate escape from human influence. It is deep, dark, remote, and separated from daily life by kilometers of water. It feels untouchable, as if climate change would have to take a number and wait patiently at the surface. But Earth does not work in isolated compartments. Changes introduced at the surface propagate downward, slowly but persistently, and even the deepest parts of the ocean are not entirely insulated from what happens above. One of the most important connections is temperature. While surface warming does not instantly heat the trench, it alters how heat moves through the ocean. Changes in surface temperature influence circulation patterns, which in turn affect how water masses are formed and transported. Over long periods, these altered currents can carry slightly warmer or differently composed water into deep regions. The changes may be subtle, but in an environment adapted to extreme stability, subtle shifts matter. Climate change also affects the amount and type of organic material sinking to the deep ocean. Alterations in surface ecosystems, driven by warming and changing nutrient availability, can change how much biological material is produced. This influences the supply of food reaching the trench. An increase or decrease in sinking material could reshape deep-sea communities, favoring some organisms over others. The trench does not produce its own food. It depends on what the surface sends down. Ocean chemistry is another pathway of influence. As atmospheric carbon dioxide increases, the ocean absorbs more of it, altering its chemical balance. These changes begin at the surface, but gradually work their way downward. Over time, they can affect deep water chemistry, influencing processes that organisms rely on. The trench's chemistry may change slowly, but it does change. Sea level rise also plays a role, albeit indirectly. Changes in sea level alter pressure distributions across the ocean floor, but while the effects are small compared to the pressures already present in the trench, they can still influence stress on geological structures over long timescales. Earth systems are sensitive, and even minor adjustments can have cascading effects. Another factor is circulation speed. Climate-driven changes can alter how quickly deep waters are renewed. If circulation slows or shifts, it could affect how long water remains in the trench before being replaced. This influences everything from oxygen availability to waste removal. Stagnation or increased renewal both carry consequences for deep ecosystems adapted to very specific conditions. What makes these influences particularly challenging to study is their timescale. Climate signals take decades or longer to reach extreme depths, and this means changes may already be underway without clear observational evidence. Scientists must rely on models, indirect measurements, and long-term trends to infer what is happening. The trench does not provide immediate feedback. There is also uncertainty about resilience. Life in the trench has survived past climate shifts, but the current rate of change is unusually rapid. Adaptations that work over thousands of years may not keep pace with changes happening over decades. This raises questions about how flexible deep-sea ecosystems truly are and where their limits lie. The idea that the trench is affected by climate change challenges a comforting narrative. We like to believe there are places beyond our reach, untouched by human activity. The deep ocean complicates that belief, and it reminds us that Earth's systems are interconnected in ways that do not respect distance or depth. This does not mean the trench will suddenly transform or collapse. Changes will likely be gradual, subtle, and difficult to detect. But subtle does not mean insignificant. Over long periods, small shifts can accumulate, altering conditions in ways that matter for survival and function. Studying these potential impacts is difficult but essential. Understanding how climate change reaches the deepest parts of the ocean helps build a more complete picture of its global effects. It also reinforces a key lesson. Isolation is an illusion. From the atmosphere to the deepest trench, Earth is a single, connected system. The Tonga Trench may feel impossibly distant from human activity, but it is not immune. It listens, slowly, to the changes above. And in doing so, it reminds us that our influence extends farther than we often imagine, reaching even the darkest, deepest corners of the planet. If Earth had an attic, deep-sea trenches would be where it stores boxes labelled "Do not throw away, might be important later." The Tonga Trench is one of those boxes. It has been quietly collecting material for millions of years, layering history beneath crushing pressure and eternal darkness. While continents erode, glaciers melt, and surface landscapes constantly reinvent themselves, the trench preserves. It remembers. One reason trenches function as time capsules is their ability to trap sediment. Material from the surface ocean slowly sinks, carrying with it chemical signatures, biological remains, and tiny mineral grains. When this material reaches the trench, it often stays there. As steep walls limit disturbance and deep isolation reduces mixing, over time layers build up, each one representing a snapshot of conditions at the time it was deposited. These layers are not just piles of mud, they are records. Chemical ratios can reveal past ocean temperatures. Certain minerals hint at volcanic activity or erosion rates on distant continents. Microscopic remains of organisms reflect changes in productivity and ecosystem structure. Reading these layers is like reading Earth's diary, written one slow page at a time. What makes the Tonga Trench especially valuable is its longevity. It has existed through multiple climate cycles, tectonic rearrangements, and biological transitions. This continuity allows scientists to study long-term trends, rather than short-lived events. Trenches provide context, helping researchers distinguish between temporary fluctuations and enduring shifts in Earth's systems. Accessing this information, however, is anything but simple. Retrieving sediment cores from extreme depths requires specialized equipment and careful handling. Cores must remain intact, preserving the order of layers. Any disturbance risks blurring the record. Even when successful, interpreting the data demands patience and cross-disciplinary expertise. Chemistry, geology, and biology all contribute to decoding what the layers mean. The trench also preserves records of events that may have left little trace elsewhere. Massive volcanic eruptions, shifts in ocean circulation, or sudden changes in biological productivity can leave subtle but detectable signals in deep sediments. In some cases, the trench may be the only place where these signals are preserved clearly. It is not just a backup archive, it is sometimes the primary one. Time capsules are valuable because they allow comparison. By examining different layers, scientists can see how Earth responded to past changes. How did ecosystems react to warming or cooling? How did carbon storage shift? How quickly did systems recover from disruption? These insights help inform our understanding of present and future changes. The isolation of the trench is key to this preservation. Surface environments are dynamic and destructive. Wind, water, and life constantly rearrange materials. In contrast, the trench is slow and stable. Processes that would erase evidence elsewhere are muted here. It is a place where history settles gently and stays put. There is also a poetic contrast at play. Trenches are often associated with destruction, with crust sinking and energy releasing. Yet they are also places of preservation. While Earth reshapes itself, it simultaneously records its own story. The Tonga Trench embodies this dual role, both consuming and conserving. Studying these time capsules is not about nostalgia. It is about understanding patterns. Earth's past is not a museum exhibit. It is a guide. The processes recorded in trench sediments are still operating today. By learning how they behaved before, scientists gain insight into how they might behave again. In this sense, the Tonga Trench is not just a deep hole in the ocean floor. It is a library. Its shelves are stacked with layers of sediment instead of books, and its stories are written in chemistry rather than words. Access is limited, and the reading is slow, but the knowledge contained within is invaluable. The deeper we look into these trenches, the more we realize that Earth has been documenting its own history all along. We are just beginning to learn how to read it. It sounds almost absurd at first. We have sent probes beyond the edges of the solar system, landed machines on other planets, and mapped distant galaxies in exquisite detail. Yet right here on Earth, there are places we understand less than the surface of Mars. The Tonga Trench sits high on that list, quietly outperforming the universe in a long-running game of hide-and-seek that humanity keeps insisting it is very close to winning. One reason space feels easier is accessibility. Once you leave Earth's atmosphere, conditions become harsh but predictable. Vacuum, radiation, and extreme temperatures, yes. But these challenges are consistent. Engineers can design around them. The deep ocean, by contrast, combines crushing pressure, chemical complexity, corrosive conditions, and constant darkness in a single package. It is like space decided to add water, unpredictability, and a personal vendetta against electronics. Distance also plays tricks on our intuition. Space is far away, but it is empty. The trench is close, but it is dense. Traveling a few kilometers downward through water can be more technically demanding than traveling millions of kilometers through space. The ocean resists motion, distorts signals, and interferes with communication. Space mostly just lets you pass through, quietly judging your life choices from a distance. Another factor is continuity of observation, and space missions often operate for years, sending back steady streams of data. Deep sea missions are short, sporadic, and expensive. We visit the trench briefly, then leave, sometimes for years at a time. Imagine trying to understand a city by visiting it once a decade for 10 minutes. That is the level of engagement we currently have with much of the deep ocean. There is also a psychological element. Humans have always looked up with wonder. The sky invites curiosity. The ocean, especially at depth, inspires caution. It is dark, hidden, and unforgiving. This affects funding priorities, public interest, and long-term commitment. Space exploration feels aspirational. Deep-sea exploration feels like poking a sleeping giant and hoping it does not notice. The trench also refuses to cooperate with our senses. We cannot see it directly. Well, we cannot hear it naturally. We cannot feel its scale without instruments. Everything we know about it comes through layers of interpretation. Data must be translated, corrected, and inferred. Each step introduces uncertainty. Space, ironically, often offers clearer views. This is why the Tonga Trench remains so poorly understood. It is not because we lack intelligence or curiosity. It is because the environment actively complicates every attempt to observe it. The trench does not just hide passively, it interferes. It bends signals, crushes tools, and limits time. It is a master of evasion. Yet this elusiveness is part of what makes the trench scientifically valuable. It represents the edge of our understanding, a reminder that exploration is not finished simply because technology has advanced. There are still places that demand humility, patience, and creativity. The trench keeps us honest. It reminds us that knowledge is earned, not guaranteed. Comparing the trench to space is not about competition. It is about perspective. Both represent extremes. Both challenge our assumptions. But the trench does so in a way that feels more personal, more immediate. It is part of our planet, and yet it remains alien. That contradiction is uncomfortable, and perhaps that is why it fascinates us. The deep ocean winning hide and seek is not a failure. It is a reflection of scale and complexity. Earth is not a simple system waiting to be fully mapped. It is layered, dynamic, and full of surprises. The Tonga Trench embodies that complexity in one of its most concentrated forms. In the end, the trench remains less understood than parts of space because it demands a different approach. Not conquest, not speed, not spectacle, but persistence. Slow progress. Willingness to accept uncertainty. As long as the ocean keeps playing hide and seek, science will keep playing along, not because it expects an easy win, but because the search itself is how understanding grows. The mystery of the Tonga Trench is not just a technical problem, it is also a human one. Our uneven understanding of Earth's extremes says as much about how we choose to explore as it does about what is difficult to reach. The trench remains elusive, partly because it exists at the intersection of low visibility, high risk, and limited storytelling appeal. In the quiet competition for attention, it loses ground before the race even begins. Exploration follows incentives. Space offers clear milestones, dramatic visuals, and a sense of outward progress. A successful mission produces images that can be shared instantly and understood intuitively. The trench offers none of that. Its discoveries arrive as datasets, pressure readings, chemical signatures, and blurred sonar outlines. They require interpretation before they inspire wonder. In a world driven by immediacy, the trench asks for patience, and patience is rarely rewarded. There is also the issue of permanence. Space missions often leave infrastructure behind: orbiters, satellites, long-lived probes. These create continuity. Deep-sea exploration is ephemeral. Vehicles descend, collect data, and retreat. Very little remains in place. Without lasting presence, knowledge accumulates slowly and unevenly, and each mission starts almost from scratch, relearning the same logistical lessons before advancing the science. Risk tolerance plays a role as well. Failures in space are expected, budgeted, and often publicly accepted as part of progress. Failures in the deep ocean feel different. Losing equipment to pressure or corrosion can seem wasteful rather than heroic. This perception shapes decision-making, encouraging conservative designs and limited deployments. The trench benefits from boldness, but boldness is harder to justify when recovery is impossible. Another factor is jurisdiction. Much of the deep ocean lies beyond national boundaries, existing in legal grey zones. Coordinating exploration requires international cooperation, shared funding, and complex agreements. These processes are slow and fragile. Space has its own legal challenges, but decades of precedent have created clearer frameworks. The trench operates under rules still being written. Data integration is another hidden challenge. Information from the deep ocean comes in fragments, collected by different teams using different methods. Combining these fragments into a coherent picture is difficult. Standards vary. Access may be restricted. As a result, knowledge grows in isolated pockets rather than as a unified whole. The trench hides not just physically, but organizationally. Cultural familiarity also matters. Humans have long used the sky for navigation, calendars, and myth. The ocean depths have no such everyday role. They do not guide travelers or mark seasons. They exist outside daily experience. This absence from routine life makes them easier to ignore and harder to prioritize. Even language betrays us. As we describe the deep ocean using words that emphasize emptiness and hostility, void, abyss, nothingness. These terms discourage curiosity by implying absence. In reality, the trench is full of processes, interactions, and history. But our vocabulary frames it as a blank, and blanks invite neglect. The trench also resists simplification. There is no single headline discovery waiting to be made. Understanding it requires assembling many small insights over time. This incremental progress does not align well with how success is often measured. The result is a paradox. The trench is scientifically rich, but strategically disadvantaged. Hide and seek implies intention, but the trench does not hide deliberately. It simply exists under conditions that filter out attention. While humanity's search patterns favor places that reward effort quickly and visibly, the trench rewards effort slowly and quietly. It is not uncooperative. It is just honest. Recognizing this changes the narrative. The trench is not a failure of exploration. It is a reminder that knowledge grows unevenly, shaped by values as much as by tools. If we want to understand the deepest parts of our own planet, we must adjust what we reward, how we measure success, and what kinds of curiosity we celebrate. The Tonga Trench keeps winning hide and seek because it plays a different game, one measured in persistence rather than spectacle, one where progress is counted in depth of understanding, not distance traveled. Until we learn to play by those rules, the trench will remain one of Earth's best-kept secrets, not because it is unreachable, but because it asks more of us than we are used to giving. After traveling through pressure, darkness, chemistry, sound, time, and technology, it is worth pulling back and looking at the bigger picture. The Tonga Trench is not just a feature on a map or a scientific curiosity. It is a symbol, a reminder that despite satellites, supercomputers, and centuries of exploration, our understanding of Earth is still incomplete. vast portions of our planet exist beyond our everyday awareness, quietly operating under rules we are only beginning to grasp. It is tempting to think of exploration as something largely finished. Maps feel complete, globes feel full. But this sense of completeness is an illusion created by surface familiarity. We know coastlines, continents, and cities well enough to navigate them casually. Yet the deep ocean remains largely outside that comfort zone. It is not that it is unknowable. It is that it requires a different kind of attention, one that values depth over speed and patience over conquest. The Tonga Trench embodies this lesson perfectly. It does not announce itself. It does not produce constant surprises on human timescales. It waits. Its processes unfold slowly, layered beneath kilometers of water and years of time. To understand it, we must be willing to slow down as well, to accept that some knowledge arrives gradually and without spectacle. This has implications beyond oceanography. It speaks to how we relate to the planet as a whole. When we assume we understand Earth fully, we risk underestimating its complexity. The trench pushes back against that assumption. It reminds us that even on our own world, that there are environments that remain effectively alien, shaped by forces and conditions far removed from daily experience. There is also humility in this realization. Humans have a long history of exploration, driven by confidence, sometimes bordering on arrogance. The deep ocean does not respond well to arrogance. It breaks tools, erases mistakes, and offers no shortcuts. Progress there is earned through respect for the environment and careful adaptation to its constraints. The trench also challenges how we define importance. It does not host cities or resources that affect daily life directly, yet it influences global systems, preserves history, and expands our understanding of life itself. Its value is not measured in immediate utility, but in what it reveals about how Earth works as an interconnected whole. Looking ahead, as the Tonga Trench represents opportunity, not in the sense of extraction or exploitation, but in discovery. It offers questions that have not yet been fully asked, let alone answered. Each technological advance, each new approach, opens a slightly wider window into its depths. The progress may be slow, but it is steady. Importantly, the trench is not going anywhere. It will remain long after current generations pass, continuing its quiet work. This patience stands in contrast to human urgency. We often seek quick answers and immediate results. The trench operates on geological time, inviting us to think beyond short horizons. In that sense, the Tonga Trench is a teacher. It teaches us about limits, about persistence, and about the value of curiosity that does not demand instant reward. It shows us that mystery is not a problem to be eliminated, but a feature that keeps science alive and evolving. As we zoom back out, the trench becomes part of a larger realization. Exploration is not something humanity finishes. It is something we continually renegotiate, shaped by tools, priorities, and imagination. The deep ocean reminds us that there is still room for wonder on our own planet, not just in distant stars. The Tonga Trench waits beneath the Pacific, unchanged by our schedules or expectations. It holds its secrets without malice or urgency, and in doing so it offers a quiet invitation to keep asking, keep exploring, and remember that Earth is still full of places where curiosity has not yet caught up.